Hi, welcome back. In this lecture I would like to provide a description of the green function that is central to the formulation of a SEM equation using integral form, and also will provide a general formulation for the method of moments. What are the Green's function? Well, a green function that we are going to call G depends on two things, on R and R prime. R is the position where we want to calculate the function, and R prime is when we have the source. So the Green's function represents the field at the position R produced by a point source at R prime. So here I emphasize a point source. Electrostatic, the Green function represents the electric potential at the position R produced by a unit charge at R prime. So for instance, we can have an electron at R prime and we want to calculate what is the potential at the position R. So R minus R prime is the distance between the 2 points. In 3 dimension, this is also written as an expression we have on this slide. So G of R prime is equal to 1 over 4 pi epsilon naught and divided by the distance. In the next slide, we are going to show the Green's function for electrostatic can be found by solving the Poisson equation. So we will go from a differential equation to the integral formulation using the Green function. So how do we find the Green's function from Poisson? So we know that the Green's function is nothing else than the potential that corresponds to a point source, somewhere. So we want to calculate what is the potential at a certain position R with a source that is a point on a position R prime. So how do we express this with the mathematical equation? Well, we know that we have our Poisson equation, and then we're going to put a source that is a pointwise. The way to represent a pointwise source is to use the so-called Dirac delta function. In 3D, the Dirac delta function is a function that vanishes for all the position R that are different from R prime. So if we are not on the source, this is 0. At the position where we have the source, this is going to be infinitely large at R prime, such that the integral of this delta Dirac in the volume surrounding this delta Dirac is equal to 1. If we eliminated the singularity, so we study this equation except for R minus R prime equal to 0, where we have this singularity, we can write our equation here in such a way. So for R, capital R greater than 0, this is a Laplacian in spherical coordinates. So the Laplacian in spherical coordinate transformed to this following equation. So this is just eliminate this part here because we're taking for all R greater than 0, and then we take the Laplacian in spherical coordinate that corresponded to this equation here. This equation has 2 types of solution. One solution is a constant that we call G1 equal to A1, and the second solution is G2 that is equal to a constant A2 over R. The solution G1 equal to A1, so the constant solution, is not of interest for us since it produces not electric field. The second solution, that is G2 equal to A2 over R, is the one we are interested in. A2 is derived by using the Gauss theorem and is equal to 1 over 4 pi epsilon naught. So we're going to substitute here the solution, our A2 in this expression here. So the textbook provides all the derivation using the Gauss law for A2. So you can look at the textbook. But this is the way to calculate in general a Green's function. So basically we put a source that has a Dirac form, and then we solve our equation. Our equation in differential form without the source, and then we basically derive the coefficient by basically imposing a continuity between R0 and R greater than 0. So one important point I want to mention here is that the Green's function derived here is only valid for the free space with no boundaries. If we want to find a Green's function with a certain boundary condition, so for instance we have perfect conductor, the Green function will be different, so will be need also to be in account. So in general, to calculate the Green's function, we are going to start from a differential equation. We have a d of f equal to s, where d is our differential operator, f is our unknown, and s is the source. So let's g, a green function, be the field at r produced by a point source at r prime that is in this case g satisfies the following equation. So as I told you, an important part is to have a pointwise source. By the principle of superposition, which holds for the linear system, we can introduce an integral, and the differential equation can be rewritten as the integral equation that is on this slide. So our unknown f can be derived by knowing just the source and the green function of the problem, and then taking this as an integral. So this is very nice, elegant formulation, right? So in case we know what is the green function of a system, that is the response of the system to a point source, we can calculate the solution for any given source given the expression for the source. So for instance, for the Poisson problem, once we know the charge density in an area and we know the green function of the system, what we can do is to calculate the potential by taking the integral of the green function multiplied by the charge density integrated on the volume. We already touched upon advantages of MoM. Well, the first is that it's very easy to deal with problems in open geometry, where differential equation solvers have big difficulties. The other advantage is that the integral formulation is efficient when the sources reside on small surfaces. So this integral, just need to take into account the charges, the sources that are in very localized part of our domain. So how do you solve the integral equation? This is the second part of the lecture, that is about the method of moments itself. So when we use the method of moments, we use a finite element methodology, right? So it's a kind of surprise. It's called method of moments, but method of moments is basically just applying the finite element method to the integral formulation of a SAM equation. So we use the finite element methodology for solving the integral equation. In this case, what we're going to do is to use a series expansion. The source, in this case, is the charge distribution, is expanded in n basis function sk, depending on r. So this is our following expression here. So we're going to represent using the finite element technique our source. So we can use either linear basis or piecewise constant basis, or like a hat function, in this case sk. And then the problem of method of moments will be to find this ak. What are the amplitude of these bases to represent our solution? So in the early application of the method of moments, the basis function were often chosen as a global function. Think about like sine and cosine, free like basis function. However, this requires knowledge of the problem, right? So some global function might be very good. So for instance, in some case, if you know that the solution of problems can be represented as a series of sine and cosine, Fourier basis is very good. However, it's not always the case. So nowadays, it's more common to divide the surface with the sources into small elements and use the finite element method. So we're going to use a local basis function. In this case, often we use the piecewise constant function. This requires less knowledge about the problem itself. Can be applied to general problem. It works much more for more general cases. So how we do? Well, the first thing what we can calculate is the potential generated by the basis. So we introduce the basis can be piecewise constant. And just for convenience of notation, we introduce the potential that is generated by a basis function, right? So what we can do is to calculate what is the potential for each of the small elements of our domain, right? So we can take our small domain that we will have a charge density, and then by using a green function, we can calculate what is the potential at each position r. Right, so this expression here is nothing other than that. Basically, given an element with a certain charge density, in our domain, we just calculate what is the contribution to a potential at a certain position. So when we take the integral, we sum it up all the contribution for all the elements, and we will calculate the whole potential. So the way to calculate the whole potential is basically take all the single sources, right? All the single sources, take the green function to calculate that particular potential that we call Fk, and then sum it up and multiply by the amplitude. That is the same one that we have been using for expanding our source. So how the procedure is working? So at the end, what we want to do is to go and get a linear system that we can solve. So the basic technique is to enforce the condition, the potential, to some potential that we know a priori. So for instance, if we know that we have a certain potential in conducting surfaces where the potential is known. And then what we're going to do is what we've done in the finite element methods, that is minimize an expression for R that is basically our expression. So here the right point, this should be multiply. Our equation that we want to solve need to be equal to 0. So we minimize to 0. So two methods are commonly used for minimizing the residual. So the first one is called point matching, also known as a collocation or Nystrom method. The second one is very much like the one that we use to get a weak formulation of our equation and then solve it in the integral form, very much like in the FEM method. So the first one is a point matching collocation or Nystrom method. The trick is that we choose some testing point Rj. So for instance, we have a domain, and then we're going to check to decide to have testing points at the center of the cell. And then what we're going to do is to impose that our potential derived by the series S function is equal to a specific potential that is given at a certain point. So we basically, for each point we know what is the potential, and then we fix this equality on these nodes. Important point is that to get a well-behaved scheme, the testing points should be chosen typically at the center points. That means that each point feels mainly the effects of one particular basis function. If it is not the case, the computed charge distribution, then a spurious oscillator behavior, because of the oscillation component of the charge distribution, are not detected at the observation points, and this gives rise to non-physical solution. So a good recipe for electrostatic is to choose rather localize function, basis function. In most of the case we use piecewise constant basis function, and then place the collocation point in the middle of each element. So we saw also in the final difference that the center is always the typical place where we want to choose our collocation point in order to avoid some spurious effects like in FD. So the second technique that we can employ to use the method of moments is the weighted residual method. In this case, we choose weighting function, very much like in the FEM method, and then we have multiplied the residual, and then we take the integral that is the weak form of our problem. Also here, we can use the Galerkin method by using Vj, by using the same basis function, in this case what we call Sk. So Galerkin weighted procedure can be seen as a way of taking up moments of the mismatch in the potential, and that's why it's called method of the moments. And that's why the electromagnetic community usually refers to the boundary element method as method of moments. So there is basically this just expression of so-called moments. An important point is that the weighted residual method is a generalization of the collocation method. So point matching corresponds to taking the test function, in this case W here, as a delta function. So we can take the Dirac, and this will correspond to taking the test function. So what we're going to do is to solve, so typically we want to solve numerically the MoM equation, and as I told you before, we need to get a linear system to solve, right? So then we are going to use MATLAB to solve the linear system. The integration required for the MoM are generally done numerically, and the singularity of green function errors not typically needs some particular attention. So both collocation and method of weighted residuals lead to n times n system of equation. So we want to have a linear system that is the following. So we want to have a matrix called A that multiplies a vector that is smaller case A equal to a source, in this case is B. So what we're going to do is to calculate what are the elements of the matrix A, that are the following, and then specifying the source term, and then solve numerically to get AK, that are just the amplitude where we multiply our source term to get the whole source. So this was this last slides. Next time we're going to look at in practice how to use the MoM to solve a practical problem that is a Poisson problem with a capacitor. Talk to you soon.